Okay, so today we're going to continue on with our hypothesis testing, and this time we're going to be looking at hypothesis testing with two samples, and we're going to be looking at testing the differences between means when we have large independent samples, testing the difference between means when we have small independent samples, and testing the difference between means when we're looking at dependent samples. So let's get started in section 8.1 first. And here we'll be looking at testing the difference between means when our samples are independent and large. Well, the first thing we need to do is we're going to be comparing two parameters from two different populations. In our case, what we're going to be looking at is the two different means. There are two different types of samples, independent samples. With independent samples, there is no regard when you're choosing sample 1 and you're choosing sample 2. They are not related in any way. As opposed to dependent samples, in dependent samples, we are matching up these two samples. So every member of sample 1 corresponds or is paired to a member of sample 2. Often, with dependent or paired samples, it's really the same person with a before and after, before a test and after a test. Visually, it looks like this. If they're independent, there's no correspondence. In fact, the sample size of sample 1 doesn't even have to equal the sample size of sample 2. Versus dependent samples, where this member of sample 1 corresponds to this member of sample 2. Now remember, this could be the same person with a before taking a cholesterol drug versus this is the same person 6 months later after taking a cholesterol drug. Excuse me. If you have paired samples, you have to have the same size of sample 1 and the same number of members of sample 2. So let's try this. If we have weights of 65 college students before their freshman year and weights of the same 65 college students after their freshman year, these two samples are definitely paired because person 1 in sample 1 is the exact same person as person 1 in sample 2. Thus, these two samples are dependent, also known as paired. Here's another example. Suppose we test 38 adult males with a psychological screening test for attention deficit hyperactivity disorder. And then we do the same thing. We sample 50 adult females with the same test. Now, clearly, this cannot be dependent or paired because the two sample sizes are not even the same. Now, if they had been the same, that does not mean that they were not dependent or independent. That doesn't matter. For independent, they can be the same size samples or not. But this one, these males are not corresponding at all to the particular female over here. Remember what I'm saying is male 1 does not correspond to female 1 over here. So that makes these independent samples. The null hypothesis, when we're looking at two sample hypothesis tests, is almost the same as what we were looking at when we were doing chapter 7 in one sample, but in this case we're looking that there is no difference between the two parameters. In other words, that they're equal to each other. And the null hypothesis also includes the equality like it did in chapter 7. Some authors always include just the equal to in the null hypothesis, but since you're used to using the less than or equal to and the greater than or equal to, these are perfectly okay. The alternative then is the complement of the null hypothesis, and it never includes equality. So less than or equal to corresponds to greater than. Equal to corresponds to not equal to. Greater than or equal to corresponds to an alternative hypothesis of less than. Here's some examples. So if the null hypothesis is that mu1 is the same as mu2 versus the alternative where the claim is they are just different, versus mu1 is less than or equal to mu2 versus we think mu1 is bigger than mu2. And we have the third version of our alternative hypothesis is that we think mu1 is less than mu2. Regardless of which hypothesis you use, you always assume there is no difference between the two population means in the null hypothesis. So to do a two-sample z-test for the difference between means, the three conditions that must be met are the samples must be randomly selected, the samples must be independent of each other, and each sample size either must be at least 30 or the populations must be normally distributed with a known population standard deviation. If these requirements are met, then the sampling distribution is a normal distribution with mu. These are three different ways to denote this. Mu of x bar minus x bar 2 is the same thing as saying mu of x bar 1 minus mu of x bar 2, but often I just write it as mu 1 minus mu 2, just kind of shortcut. The standard error now looks complicated, but it's really not. This is the standard deviation squared, or also known as the variance of sample 1, divided by the sample size of sample 1, plus the variance or the standard deviation squared of sample 2, divided by the sample size of sample 2. Once you do these two divisions, then add those numbers together, and then take the square root of that. That's known as the standard error. The sampling distribution is a normal distribution, so it has the bell-shaped curve. My test statistic is x bar 1 minus x bar 2, and to standardize that, I get z is equal to x bar 1, the sample mean of sample 1, minus the sample mean of sample 2, minus 0. This is always, if you don't think they're different, then their difference is 0, so this is always 0. So really, my numerator only includes this piece of it, divided by the standard error, which remember is the variance of sample 1, or the standard deviation squared of sample 1, divided by the sample size of sample 1, plus the standard deviation squared of sample 2, divided by the sample size of sample 2. Add these two together, then take the square root. If the sample sizes are large enough, you can substitute the sample standard deviation of 1 and the sample standard deviation for 2 in place of the population standard deviations. So in words, the first thing we want to do is we want to state the hypotheses. Then we identify the significance level, which will be given in the problem. The sketch the sampling distribution, in other words, sketch the normal distribution, the bell curve. Determine the critical values and you determine them from table 4, which is the standard normal table in the appendix. Determine the rejection regions. Find the standardized test statistic. Compare that to the rejection region, and if the standardized test statistic is inside the rejection region, then we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. So let's look at an example. So a credit card watchdog group claims that there is a difference in the mean credit card debts between households in New York and Texas. Now notice, they're only testing that there is a difference between them. They're not saying one is greater than the other. So our alternative hypothesis is just going to be that the two means are different. Here's our summarized sample data that was taken, and these two samples are independent. So let's get started. The null hypothesis is mu1 is the same as mu2 versus mu1 is different than mu2, not equal to. From the problem, we saw that the significance level was given to be 0.05, and N1 is 250 and N2 is 250. To find the critical values and the rejection regions, we take the significance level 0.05 because the alternative is a two-tailed test. We split the 0.05 in half, and we put half of alpha, which is 0.025 in the lower tail, and half of alpha, 0.025 in the upper tail. Then we get to go to the standardized test statistic. We look through the body of the table for 0.025, or the closest to it, and we find the closest to it is a z-value of negative 1.96. By symmetry, the positive critical value is positive 1.96. Anything below negative 1.96 or above positive 1.96 is the rejection region. Then we calculate the test statistic, which is sample mean 1 minus sample mean 2 minus 0 divided by the standard error. This came from the square root of the standard deviation of sample 1 squared divided by 250 plus standard deviation of sample 2 squared divided by 250. You added those two fractions together, took the square root, which was 108.5983. Do this division here, and you get a test statistic of negative 1.11. Well, negative 1.11 is about here, which is not inside my rejection region, which is the blue areas over here. So my decision is to fail to reject the null hypothesis. In other words, at the 5% level of significance, there is not enough evidence to support the group's claim that there's a difference in the mean credit card debt of households in New York and Texas. Okay, thank you. And that is the end of our lecture on 8.1. Please go and work the problems on the Course Compass website for section 8.1.